Hello everyone. So till now in multi-degree of freedom system, we have seen how to set up the equation of motion. Now the next step is to learn methods to solve those equations of motion to get the response of a multi-degree of freedom system. When we considered single degree of freedom system, we saw that there is only one way in which a single degree of freedom system can respond. However, a multi-degree of freedom system, which is made up of several degrees of freedom, can respond in multiple ways, and the total response actually is combination of different type of responses that the structure can uniquely respond in, and we are going to look into that. So we are going to also learn about mode shapes, which basically reflects or which basically describes one of the ways in which a structure can reflect. And we are also going to learn about frequencies. Now a multi-degree of freedom system would have multiple frequencies, so we'll see that how to actually find out those frequencies. Okay, so let us get started. We have already studied how to set up the equation of motion of a multi-degree of freedom system, and we saw that now the forces are represented in terms of vectors and the displacement are represented in terms of vectors, and there are mass matrices and stiffness matrices. So as against to a single degree of freedom system, okay, we set up the equation of motion for a multi-degree freedom system in terms of these forces, okay, and we saw that how we can get the mass matrix, the damping matrix, and the stiffness matrix as this. Let us see, once we have obtained our equation of motion as this, okay, how do we solve this equation of motion? Okay, can we employ the same analytical solution that we have derived for single degree of freedom system to solve the multi-degree of freedom system? Okay, and if we can, then how do we do that? Okay, so first thing that we are going to talk about is basically free vibration. Okay, and let us first consider undamped free vibration. So my damping matrix is 0 and there is no external force, so I am considering that 0. So my equation of motion becomes mass times acceleration vector and then k times displacement vector to be equal to 0. Okay, all right. So we are going to discuss about the solution of this equation, but to get into that, first we need to discuss some basic characteristic of vibration for a multi-degree of freedom system. Okay, now we know that for a single degree of freedom system, let me just draw it here. Okay, I had only one degree of freedom u, and there was only one possible way in which a single degree of freedom system could move. So by definition, I needed only one degree of freedom to represent the deformed position, okay, with respect to its initial equilibrium position. However, let us consider, okay, a 2 degree of freedom system, something like this. Okay, so such that I'm going to consider different 2 degrees of freedom such that the total mass remains the same. Okay, however, the distribution is different little bit. So let me draw in the first, let me draw the 1 degree of representation. This is the 1 degree of representation of a system. Now let us consider, so there is only one way it can deflect, right? We saw that we only consider deflection like this. So if it's a deformable, consider deflection like this. Okay, so we know how it would deflect. However, let us consider system like this, in which I have two masses, okay, which are joined first from the support to the first mass. I have, consider the same stiffness here, stiffness K and stiffness K. However, mass M1 and M2, and M1 is greater than, much greater than M2 here. In the second case though, let us consider a different representation. So again, in this case I have M1, M2, and in this case M1 is much smaller than M2 here. Okay, and in the third case I'm going to consider M1 and M2 which are comparable to each other. Okay, as you can imagine, physically if you look at it, there are multiple ways, or in this case if it's a 2 degree of freedom system, okay, there are two ways in which this structure or this system can deform. One would be simply like this. However, if this mass is very heavy, then it is likely that the movement of this mass is going to dictate the overall response. Okay, now compare this to the second system that I have drawn here. In this case, if the mass M2 is much larger than mass M1, then the overall response is going to be dictated by the movement of mass M2. Okay, but in general, reality lies somewhere in between, where mass M1 and M2 are comparable, and basically the deformation or relative deformation of both M1 and M2 actually going to dictate the overall response. Okay, and for 2 degree of freedom system, it can either respond like this or it can also respond like this. So there are only two ways in which this structure can deform in 2 dimension. Okay, so for multi-degree of freedom system, okay, the total mass and the stiffness are not the only parameter. The distribution of mass and stiffness also plays a role. And we saw that for the distribution of mass here, I can do the same thing where I keep the masses same, but I consider different stiffnesses. Okay. And in this case also, we can imagine that depending upon the stiffness between the masses and the support, okay, the overall response is going to change. Okay, now in previous chapters we saw that we used to assume a deflected shape of a continuous system and utilize that, which we called as a shape function, and utilize that to reduce it to single degree of freedom system. Okay, but that was an approximate method, and we assume that the deflected shape can be represented by static deflected shape or some other function. However, through the analysis of multi-degree of freedom system, okay, we wish to find out what would be the exact deflected shapes of a multi-degree of freedom system. Okay, and to get that, okay, we are going to do or solve the equation of motion that we have just written here. Okay, now, so as you can imagine, the total response of a multi-degree of freedom system, okay, depends on the distribution of mass and the distribution of stiffness. Okay, and it can deflect in multiple ways depending upon the number of degrees of freedom. Okay, so the total response, okay, so let us say I have the total response as vector u, can be written as linear combination of different deflected shapes. Okay, so let us say this is phi 1. Okay, so I'm using phi 1 to represent a deflected shape. This is similar to the shape vector that we had used in previous chapters. So let us say I have a deflected shape which is something like this. Okay, linearly increasing with height. So if the height is h here and height is h, then this deflected shape can be written as, okay, half and 1, where this is the first degree of freedom and this is the second degree of freedom. Similarly, if I have a deflected shape, okay, which looks like something like this, okay, I can write my phi as, let me say, -1 and 1. All right, so these are some of the possible ways in which a system can deflect. Now this is a 2 degree of freedom system. You could have multiple degree of freedom system, okay, and there could be different shapes. So these are the possible ways in which a structure can deflect, but I still don't know that which deflected shape is going to be the close or going to determine the overall response. So what do? We consider all deflected shape and we say that the total response is actually going to be sum of all such deflected shape, okay, a linear combination, okay, and these factors actually determine the relative contribution of each of these mode shapes to the overall response. Okay, so this is how I imagine my multiple response of a multiple degree of freedom system, and we are going to see how to find out these shapes exactly and how to find out these factors. Okay, so let us start with an example of a 2 degree of freedom system. Okay, let us say this is m1 m2 and this is k1 k2. Okay, and let us say it has been given some vibration, initial vibration. Okay, so it might be given some initial displacement. Okay, let us say it looks like something like this. All right, so this is the initial displacement at these 2 degrees of freedom. Now if we give initial displacement to these two masses and then plot the resulting motion from these two masses, we are going to see that, okay, in general the motion of these masses are not harmonic. Okay, similarly for this, so this is u1 plotted against time and this is u2 plotted against time. Okay, so if I give some initial displacement to a multi-degree of freedom system and let it vibrate, the response of each degree of freedom in general is not harmonic. Now compare that to single degree of freedom system, in which when we provided initial condition u0 and u dot 0, we said that the resulting motion would be harmonic and it was given as u0 cos omega nt plus u dot 0 divided by omega n sine omega nt. Okay, but that is not the case here. Okay, so in general the resulting motion is not harmonic, plus as these two masses m1 and m2, okay, vibrates, we will see that the structure or this 2 degree of freedom system here, the shape of this 2 degree of freedom system is going to change with time. Okay, so after some time it may look like something like this, okay, or it may also look like something like this. Okay, so the shape is actually going to change. Okay, but okay, there is a possible combination of initial displacement given to these degrees of freedom, okay, such that if this 2 degree of freedom system given initial displacement in such a fashion, okay, there exists a combination of u10 and u20 such that the resulting motion is actually going to be harmonic. So let me redraw it with initial displacement. This is going to be harmonic. Okay, and u1 is also going to be harmonic. Okay, so there exist few combinations, okay, such that if the motion is initiated by providing those initial displacement to each degree of freedom, then the resulting motion of each degree of freedom is actually harmonic. Okay, those combination of degrees of freedom or those combination of initial displacements are actually called characteristic shape, or also called mode shape, okay, of a multi-degree of freedom system. Now for 2 degree of freedom system, we would have two such characteristic shapes or mode shapes, such that if it's given the initial displacement, okay, with those proportions, then it would have resulting motion at the degrees of freedom which would be harmonic in nature, plus it would maintain its shape. Okay, so for example, this 2 degree of freedom system, okay, if I give initial displacement like this, okay, it is going to vibrate such that it maintains its shape. Okay, so if you can look at here, the relative, okay, at any time t, the relative shape of the structure is not changing. Okay, of course that overall amplitude is changing, but the relative shape is not changing. Okay, and if I have an n degree of freedom system, then I would have n such characteristic shape. For example, this is the first characteristic shape or first mode shape. Okay, second mode shape could be something like this. Okay, I can have something like this, then something like this, and then so each of these, the shape is actually not changing. So this is second mode shape. Okay, so let us just recap. Okay, we said that in general, if you initiate the motion, the free vibration motion of a multi-degree of freedom system by providing initial displacement to different degrees of freedom, the resulting motion at each degree of freedom would not be harmonic, and the structure is going to change its shape at each time instant. Okay, however, there exist few characteristic shape, okay, with which if the initial displacements are assigned proportional to those characteristic shape, then the resulting motion is going to be harmonic, plus the structure is going to maintain its shape. Okay, those characteristic shapes are called mode shapes. Okay, or and a n degree of freedom system would have n such mode shape or characteristic shapes. Okay, all right, now we define for a single degree of freedom system the natural time period as 2 pi under root m by k. The question comes, how do we define, or analytically we said that it is time taken to complete one cycle of motion, okay, for vibration. Now, as I said, in general, the resulting motion here is not harmonic, right? So then how do we define this time period for a multi-degree of freedom system? Okay, so for a multi-degree of freedom system, the time period is not defined for the overall response, but it is defined for each mode shape. Okay, so the time period we define for each mode shape. So let us say I have T1 here for the first mode shape, and then T2 here is the second mode shape. Okay, and T1, or let us say a natural time period of vibration, natural time period of vibration is basically the time taken to complete one cycle of vibration in a particular mode. Okay, so T1, T2, T3 like that for a multi-degree of freedom system. Okay. Now, as we have previously studied, okay, these relationships still hold. The Tn would be 2 pi by omega n, or frequency would be 1 by Tn. Okay. All right. So we have defined, or we have discussed, that how a structure can deflect in multiple ways. Okay, in general, if we initiate the motion by providing initial displacement and velocity or whatever, okay, the resulting motion at each degree of freedom is not harmonic, but there exist some shapes according to which, if the structure is assigned initial deflection and allowed to undergo free vibration, then in those cases the resulting motion would be harmonic and the structure would maintain its shape while vibrating in those characteristic shape. Those are called mode shapes. Okay. So as we have discussed, the total response of a multi-degree of freedom system can be represented as some linear combination of each mode shape. Okay, so let us say I have n degree of freedom system, so it would be some linear combination of first mode shape, then second mode shape, okay, like that. All right. Now, the free vibration response of a multi-degree of freedom system, the total response ut, okay, in the nth mode, let us say this is the nth mode, can be written as the mode shape. So I'm just considering one of these mode shapes. Okay, let us consider the contribution of the nth mode shape to the total response by writing it as un of t, and that would be equal to phi n, the mode shape, times the time variation qnt. Okay, and that we have previously also discussed, that if the deflected shape of a structure is represented through some shape function, okay, then the total response can be represented as a product of that shape function times some time variation function that represents the evolution in time. Okay. Now, as we have said, this phi n is actually constant in time, it does not vary with time. Okay, so the time variation is actually represented by q and t. Okay, and this q and t, okay, as we have said, that if it is vibrating in one of its mode shape, the resulting motion would be harmonic. Okay, so can I say that q and t can be written as an cos omega nt plus bn sin omega nt. This is the general equation of motion for the vibration, or general equation of motion for the harmonic vibration. Okay, an cos omega nt plus bn sin omega nt, and this is for the nth mode. All right. So the response contribution in the nth mode can be represented as shape factor for the nth mode, or mode shape, times q and t, which we have written as an cos omega nt plus bn sin omega nt. Okay, and our equation of motion for free vibration is this. Okay, so what we are going to do here, we are going to take this, okay, and substitute in this equation of motion. Now if I double differentiate this term here, okay, let us see what do we get. Okay, so un equal dot t would be basically equal to phi n times, if this is differentiated twice, it would be the same function times minus omega n square. Okay, so I'm going to write down minus omega n square times here, and this becomes qn of t. So I'm going to substitute that here, I get mn, m as this, alright, times q, which I'm going to write this as and phi n, and then q and t, plus k times u, which would again be phi n times qn of t. Okay, and this can be further written as k matrix times phi n minus omega n square times m times phi n times q and t. Now, this equation tells us that either q and t can be equal to 0, okay, which means that there is no motion, okay, and which is calls like trivial solution. So we are not bothered about that. Okay, we are the only thing that is going to give us meaningful solution in this one when we consider k phi n is equal to omega n square times mass matrix times phi n. Okay, if you look at this carefully, this is of the form a vector times a vector x is equal to some lambda times another vector b times x. Okay, this is called eigenvalue problem. Okay, and you may have come across this kind of problems in your advanced numerical methods course or mathematics course, okay, or matrix algebra course. Okay, so this is basically eigenvalue problem. Okay, now in this equation my K matrix is known to me, my M matrix is known to me. Okay, so remember, if I have a multi-degree of freedom system, okay, something like, let us say this K2K, I know how to get my K matrix, right, which in this case would be simply 3K minus K and K, and M would be 2M 0 0 M. We saw that how to get these matrices. So in general, if the structural properties are given, my K matrix is known to me and my M matrix is known to me, the unknown parameters are actually omega n square and the mode shape phi n. Okay, and through this eigenvalue problem, okay, we are going to solve for these unknown parameters. Okay, so basically, let me rewrite that k minus omega n square m, okay, times phi n is equal to 0. Now in this case, this would have a non-trivial solution, okay, if this term here is equal to 0. So this is like solution of n simultaneous equation of motion. Okay, and because this is homogeneous, okay, one solution could be the phi n equal to 0. Okay, that is the trivial solution. So for non-trivial solution, we need to have this equal to 0, or specifically not this actually, but the determinant of the coefficient of the phi n vector, okay, is equal to 0. So you can either write determinant of this or you can just use this equal to 0. Okay, this is how we get the solution to an eigenvalue problem. Now if, let us say, these are n homogeneous equation, then this would give me, okay, remember the constant here is omega n square, not omega n. So this gives me an algebraic equation, okay, of nth power of this constant here, which would be omega n square, okay, to the nth power. So it would have n roots, which would be real and positive because my K matrix and N matrix are usually real and positive, definite and symmetric. Okay, so in that case I would have n roots here. Okay, so we can solve those type of equation of motion and we can find out the frequencies, okay, omega 1, omega 2, so on. Okay, and typically we arrange it like omega smallest frequency first. Okay, or if you want to write in terms of time period, we'll have time period t1 t2 and rearrange it so the largest time period mode is first. Okay, this is just a convention. Okay, the first mode is also called the fundamental mode. Okay, and once we have found out all these roots, omega 1, omega 2, remember it will give you omega n square 1, omega n square 2, but then you can take the square root and find out omega n, omega 2 and so on. Okay, so once you get that, you can substitute it back to this equation. Okay, and you can find out the shape function phi 1, phi 2. Okay, or more specifically the mode shape here, the shape vector phi 1, phi 2 and so on corresponding to each frequency. Okay, and that through this procedure we can find out the exact mode shapes and frequency of a multi-degree of freedom system. Okay, and let us take one example to see how do we do that. Okay, so I'm going to take example of just what we have seen above. I have a 2-degree of freedom system with storage stiffnesses as k, 2k and k, and this is 2m and m. So the mass matrix I had assembled as 2m 0 0 m, and the stiffness matrix I had assembled as 3k minus k and k. So let us see, okay, what are the modal frequencies and modal shapes for this 2-degree of freedom system. So our equation was k minus omega n square m, determinant of that is equal to 0. Okay, so let us substitute that and see what do we get. So I have here 3k, okay, and then minus k here, and k here, and this is omega square times 2m 0 0 m here, and the determinant of this whole thing. So I basically get as 3k minus 2m omega square minus k, here again have minus k here, and k minus omega square m, and this determinant to be equal to 0. So the equation that I get is 3k minus 2m omega square times k omega square m minus k square, and this is equal to 0. So this would give me a quadratic in omega square. Okay, and let us see what that equation is. Okay, so it would give me here 2m omega 4 minus 5 km omega square plus 2k square equal to 0. So omega square is minus 5 km plus minus 25 k square m square minus 16 k square m square divided by 4 m. Okay, so basically omega square is, this is 9 km square here, which under root would become plus minus 9 km. Okay, so what do we have here? Remember this is plus here because this is minus, so 5 km plus minus 3 km. When we take outside the root, this would become 3 km divided by 4m. So first let us take the smaller frequency omega 1 square, and it would be k by 2m, and omega 2 square is 2k by m. Okay, so omega 1 is k by 2m and omega 2 is 2k by m. Okay, so we've got the two frequency of this 2-degree of freedom system. Once we have that, let us substitute back in the equation the characteristic equation, or not the characteristic equation, but the eigenvalue equation, k times phi n minus omega n square. Okay, or I can write it simply like this: k minus omega n square m, okay, times phi n is equal to 0. So let us first get the first mode shape. So I can substitute omega 1 equal to k by 2m, or omega 1 square equal to k by 2m. Once I substitute that, let us see what do we get. Okay, so basically I would have these expressions inside, and if I substitute omega square equal to k by 2m, this would be simply 2k minus k, and then here k, so it would be k by 2. This times phi 1. Okay, now phi 1 can be written as phi 11 and phi 21, which basically represents the coordinates at the degree of freedom 1 and coordinates at degree of freedom 2 for mode 1. So remember, if you have phi j, the I corresponds to degree of freedom and j corresponds to the mode, and the same would be true for other response vectors as well, like uij, okay, and so on. So I have phi 11 and phi 21 equal to 0. Okay, so the equation basically I get is 2k phi 11 minus k phi 21 equal to 0, or minus k times phi 11 plus k by 2 times phi 21 is equal to 0. Now if you look at carefully, both of these equations are one and the same. Okay, the second thing you are going to notice, okay, you can only get solution for this vector in terms of some multiplicative constant. Okay, for example, your phi 21, or let us say phi 11 is nothing but 1 by 2 phi 21. Okay, so here, because the homogeneous equation, it can have infinite solutions. Okay, so you can only get solution for these mode shapes which are in terms of some multiplication factor, and that is okay, because when we represent a shape factor or a mode shape, okay, these are always the relative location of each degree of freedom. Okay, so what we do typically in these cases to get the mode shapes, okay, we normalize these mode shapes somehow, okay, such that we assume or we find out the individual elements of these mode shapes. So one of the ways in which we can normalize, and especially if it's a representation of a multi-story building, is that we can normalize it with respect to the top story degree of freedom. Okay, so let us say we assume it to be 1, which for phi 1, remember, for phi 1 this quantity is phi 21 and this is phi 11. Okay, for phi 2, okay, again the same quantity would be phi 22 and phi 12 for the second mode. Okay, so let us first deal with the first mode. So if I assume my phi 21 equal to 1, my phi 11 become half. So my first mode shape I get as half and 1. Okay, similarly I can substitute my omega 2 square equal to 2k by m, and we'll see I can get my second mode shape as minus 1 and 1. Again, in the second mode shape, we are normalizing with respect to the second coordinate. So this would look like something like this. The first, remember, this one is phi 1 2, this one is phi 2 2. So first degree of freedom and the second degree of freedom. So this is minus here, so let us consider in this direction, and this is plus here, so this would look like something like this. Okay, so in both cases I have normalized it with respect to the top story modal coordinate. Okay, And there are different ways in which you can normalize it. You can normalize it with respect to some specific degree of freedom. Okay, or you can also normalize it with respect to some other method. We will see that later. Okay, so using this procedure, we can get the mode shape and the frequencies of different modes of a multi-degree of freedom system. Okay, all right. Now remember, here in a multi-degree of freedom system, we would be doing lot of matrix algebra. Okay, and it would be very easy if we learn or if we employ some of the techniques and the properties of these mass matrices, stiffness matrices, mode shapes, so that it becomes or it makes the job easier for us to solve some of the equation of motion. Okay, so let us learn some of the specific properties and some special matrices that we would be using to actually analyze multi-degree of freedom system using matrix algebra. Okay, now remember, for an n degree of freedom system, I have said that I would have phi 1, phi 2 that represents the mode shapes, okay, of each mode. Corresponding to that, I would have the frequency for each mode shape as well. Okay. What I can do, I can combine all these, okay, mode shape vector. Remember, right now each of them are a column vector. I can write a mode shape matrix for which each column is actually one of the mode shape vector like this. Okay, so the overall matrix is basically representing columns that are the mode shape of a n degree of freedom system. Okay, and we also write this as phi jn. Okay, just to represent. Okay, this is called modal matrix. Okay, modal matrix. Similarly, I'm going to define a diagonal matrix represented through this quantity here, okay, omega square. In this, each diagonal element is actually the frequencies of that individual mode, and the off diagonal term are 0. Okay, and remember, I'm considering frequency square because my eigenvalue is actually frequency square. Okay, the lambda in that eigenvalue equation is actually frequency square. So I'm going to define a matrix for which the diagonal terms are the frequencies square of each mode shape, and this is called spectral matrix. Okay, now let us get back to our eigenvalue equation, which was k times phi n is equal to omega n square times m times phi n. Okay, or maybe we can write omega n square here. Okay. Now, this is the equation, the eigenvalue equation for the nth mode. Okay, we can combine all the modes together. Okay, so remember, this is for the nth mode. For an n degree of freedom system, I would have n such equations, n such separate equations. Okay, we can combine all those equations in a single equation. Okay, so that I can write for all modes matrix K times not the mode shape phi n, but the modal matrix phi n is equal to mass matrix times the modal matrix times the spectral matrix. And this basically represents the same thing. This would have, if you expand it, n such characteristic equations, okay, for n degree of freedom system. Okay, so this is just a compact way of writing all the characteristic equation of the eigenvalue problem for all the modes of a multi-degree of freedom system. Okay, all right. Now let us look at a very important property of the mode shapes, which is going to help us immensely in solving the equation of motion for a multi-degree of freedom system. Okay, that property is called orthogonality of modes. Okay, orthogonality of modes. Okay, now the orthogonality of the modes states that, okay, the different modes, okay, different modes corresponding to different natural frequency. Okay, so different modes, let us say, corresponding to different natural frequencies okay, can be shown to satisfy the orthogonality condition, which is basically if I take a mode shape n and take a transpose of that and multiply it with the mass matrix times the mode shape of another mode, okay, this would be equal to 0. And the same condition can be shown for the stiffness matrix as well, that if I take a stiffness, if I take the mode shape transpose of a mode shape n multiply with the stiffness matrix times another mode shape, again this would be equal to 0. Okay, and mathematically we can prove this. Okay, let us see how we can do that. Remember that I can write for my nth mode, okay, for the nth mode I can write my eigenvalue equation as k times phi n, okay, equal to omega n square times m times phi n. Okay, this is for the nth mode. Similarly, for the rth mode, which is a mode that is different from the nth mode, I can write down a similar equation. K times phi r is equal to omega r square m phi r. Okay, not a matrix here, it is a vector. Okay, now what we can do here, okay, we can multiply, okay, any of these equation with the transpose of other mode. So let me say, let me multiply this with phi r transpose on both side of the equation. Okay, so that I have omega n square phi r transpose, and then okay, here also I am going to multiply this phi n and omega r square phi n. So our nth mode with the phi r to the power transpose and the rth mode phi n to the transpose on the both side of equation. Okay, then I can take basically the transpose of one of the equations. So let us say I take the transpose of this equation on the both side. Remember, if a matrix is symmetric like M or K matrix, if you take the transpose of this, it would be same. Okay, and if you take transpose of two matrix, it would be transpose of the second matrix times the transpose of the first matrix. So I'm going to employ these rules here. Okay, so if I take transpose of the equation 1, I would get as phi n transpose times k times phi r is equal to omega n square, okay, times phi n transpose times n times phi r. Okay, So let us say this is equation 2 and this is equation 3. So now if I take equation 2 minus equation 3, okay, these two quantities are same, right? And this can be written as omega r square minus omega n square times phi r equal t times m times phi r. Okay, sorry, this is n here, and this equal to 0. Now we have said that these two are different modes. So basically, if omega r is not equal to omega n, then this term would be here, that would be equal to 0. So then phi r is equal to 0. Okay, and this is basically the orthogonality condition. Okay, now we have written this for mass matrix. Okay, we can derive the same expression for the stiffness matrix as well, just by writing this expression as phi and t, and the mass times phi r would be K matrix times phi r divided by omega r square. That would be equal to 0. So this would effectively become phi n k times phi r is equal to 0 as long as this condition is satisfied. Okay, so this orthogonality condition is a very powerful basic conclusion that we utilize to solve our equation of motion. We'll just see after discussing this. Okay, now if these conditions are satisfied, let us define, okay, two square matrices like this. A square matrix K, which is the stiffness matrix. Okay, K is defined as the shape factor or the modal matrix transpose times the stiffness matrix. So this is capital K here. Okay, times this. Now look at this quantity here, and similarly we are going to define a capital mass matrix as well, which is basically the product of phi t times mass matrix times phi. Okay, now if you look at carefully here, what do you have? The modal matrix, which I have previously written as each column vector is basically phi 1, each one of the modes phi 2, and then you have phi n here. Okay, and then you have the stiffness matrix, which would have term k11, okay, k12 and so on, k21, okay, so on. So let us say just the general elements here, and then phi, okay, here remember I have transpose here, okay, transpose here. So this one is actually phi 1 t, not t here, just write down the phi 1, phi 2 and so on, phi n here. Okay, now if I multiply these elements here, what you will see that for any ith jth term, what I will get as in this case, so phi I of transpose times the matrix K, this overall matrix, okay, times phi 1, phi j, let us say here. Okay, so this is any ith jth term. Now if it is the diagonal term, then I can write it as phi ii, and any off diagonal term I can write it as phi t, k and phi j. Okay, where I is not equal to j. Now if you look at carefully, using orthogonality property, this I and j, wherever they would be different, those terms would be equal to 0. Okay, the non-zero terms would only exist as long as the phi I and j would be both equal to, let us say in this case I. So only the diagonal terms are going to exist here. Okay, and those diagonal terms can be written as kn. So if you consider the nth diagonal term, okay, the Kn can be written as phi n transpose times K times phi n. So this matrix is actually a diagonal matrix, and each element of these diagonal matrix can be represented as Kn equal to mode shape transpose times K times the same mode shape. Similarly, for the mass matrix as well, I would get a diagonal matrix, okay, and the nth element of that diagonal matrix can be written as phi n transpose times the mass matrix times phi n, and both these are obtained utilizing the condition of orthogonality of the mode shapes. Okay, so Kn is now known to me, so the nth element of these diagonal matrices are now known to me, and they are again related by the same expression Kn is equal to omega n square n, which you could easily obtain if you just substitute Kn phi n is equal to omega n square mass times phi n. Okay, and then combine the terms and write it as Mn. Okay, so the diagonal terms of these matrices K and M are related using this equation right here. Okay, so now the question comes, okay, why we are getting into all these diagonal matrices? Why do we need condition of orthogonality and everything? Okay, so to explain that, okay, let us consider first a 2-degree of freedom system. Okay, remember, for single degree of freedom system, the equation of motion was this cu dot plus k equal to 0. Okay, so this was a second order linear differential equation, and I could directly solve it. I had only one variable u, okay, and I needed to solve it u as a function of t. Okay, but now if I have a 2-degree of freedom system like this, let us say m11 m, so basically now first let me write down the equation in terms of matrices. So m mass matrix times acceleration, then let us say stiffness matrix times displacement vector is equal to 0. In general, I would have elements in the mass matrix as m11, m12, m21, m22. Okay, and this is u1, u2. Similarly here, k11, k12, k21, k22. Okay, and this as u1 and u2, and this equal to 0. So when I write down, it will give me two simultaneous equation, right? Which is basically m11 times u1 double dot plus m12 times u2 double dot, then k11 times u1 and k12 times u2 is equal to 0. Similarly, m21 times this acceleration, and then m22 times the acceleration here, k21 u1 plus k22 u2. The question is, how do we solve these two differential equations? Okay, these are two simultaneous differential equations and these are coupled. Okay, the first equation has term in u1, u2 both, and the same for the second. So I cannot directly solve this differential equation. Okay, had they been uncoupled differential equation, then it would have been a lot easier for me to directly solve this in some terms of some parameter, but that is not the case here. Okay, but just imagine, okay, if I have diagonal matrices which only have diagonal element, and then u1, u2. So let us say this is m1 here and this is m2. Okay, and this is k1 here and this is k2. So no off diagonal terms. Now, if the mass matrix and the stiffness matrix are diagonal matrix, then what do I basically get? m1 u1 dot plus k1 u1 equal to 0, m2 u2 dot plus k2 u2 equal to 0. And now the equations are uncoupled, right? So if I have an n degree of freedom system, I get n coupled differential equations which are coupled through the mass matrix and stiffness matrix, and if somehow I can diagonalize the mass matrix and the stiffness matrix, then I can uncouple those equations of motions, and then I can solve n differential equation individually like single degree of freedom system, okay, for which we already have standard results available. Okay, and that is what we are trying to achieve by utilizing the condition of orthogonality of the mode shape, and by constructing matrices in which the elements, the mass and the stiffness elements are diagonal. Okay, so although here it is not exactly u1 q1, because remember u1 is your phi times q1. Okay, so these becomes like a differential equation in terms of q1, but the idea is if you have mass and the stiffness matrix diagonal, then I can get n uncoupled equation and I can solve the multi-degree of freedom systems as n single degree of freedom systems and n differential equations. Okay, and for which the analytical results are already available to me. Okay, all right. So with this, I'm going to end this chapter here. Okay, in next chapter we are going to see how to actually utilize the mode shapes, okay, and the frequencies to actually get the overall response of a multi-degree of freedom system. Okay. All right, thank you very much.